So, Bismillah ar-Rahman ar-Rahim, this part talks about dynamic routing protocols, and as we have, and as I said, dynamic routing protocol is one class of routing protocols where the topology of the network may change at any point in time, and the routers need to exchange some information so that they are updated all the time with the current topology of the network. So the main functions of the dynamic routing protocols are as follows. First, the dynamic routing protocols are used for sharing information amongst the routers. So depending on the routing protocol that you use, each routing protocol creates some kind of a message with a specific format, and they keep exchanging these messages between the routers. The purpose of these messages is just to inform the routers that there is some kind of a topology change, or some networks are connected to a specific router, and so on. So depending on the routing protocol that you use, this message would have a specific format, and they would be exchanged given some time intervals, which might be different depending on whether you use RIP or OSPF or ERGRP and so on, as we will see later. Oh, sorry. Okay, so the dynamic routing protocol exchange this information. This information will facilitate the automatic discovery of any topology change in the network. So this is unlike the static routing protocols. Static routing protocols do not discover automatically any routing, any topology change. The system administrator needs to manually change the configuration of the routers every time there is a topology change. But dynamic routing protocols, the main purpose of it is just by exchanging these messages between each other, they can be updated right away once there is a topology change. So that's this point. Automatically update routing table when the topology changes. So based on this exchange of information, and based on the knowledge of the topology change, now we are in a position to determine what is the best path if we want to send from one router to another router. What is the best path? Should we go this way or should we go this way? Okay, what is the best path? Again, in static routing protocols, it depends on the preference of the system administrator. It depends how the system administrator configures the router. The router may send specific packets to a specific path, which is not necessarily the best path. Okay? So depending on how the system administrator configures the router will do what's asked to do. But the dynamic routing protocols will always look for the best path from any 2 points. Okay? Based on collecting some knowledge about the network topology. Okay? So these are the three main functions of a dynamic routing protocol. The main components of any routing protocol is divided into two major parts, or maybe we could say three major parts. One part is the algorithm, and the algorithm is the one that facilitates the exchange of messages and determines the best path based on the collecting these messages. Okay? These messages themselves, these are the messages themselves, they include information about the topology of the network. So there is message exchange part. In the message exchange part, there is some messages that gets exchanged between the routers. This message consists of some information related to the topology. So for example, this router here, it sends some routing messages to this router to inform it that I have direct connection with this LAN, okay? And this LAN information is whatever. This is like an Ethernet LAN, or this is whatever, Wi-Fi or whatever. So this router will send to this router some information about this, the LAN. The LAN is directly connected to this router. Similarly, this router will send to this router information about this LAN. Okay? So if this router wants to send a message to this LAN, then it knows that it doesn't have direct connection to it, but it can send to R1, and R1 will deliver it. Okay? So the routing protocol messages are the messages that contain the information about the LANs or the networks that are directly connected to the router. And then when I run the algorithm will then decide if I want to send to this LAN, then I need to go to this direction. Of course, I could have a different path to the same LAN, right? So this router can go directly to router 1, or can go to the same LAN through router 3 instead. So the algorithm is the one that decides that. Okay? So messages are just, some format of the message that exchange some information about these networks. And then the algorithm decides whether I go this way or go this way. And it will always select the best path based on some criteria, because best path can be decided upon, use different criteria. So we'll talk about what are the types of criteria based on which we decide that this is the best path. And it's different from one routing protocol to another, as we will see. Any questions so far? So, of course, dynamic routing protocol came about to just fix the problem related to static routing protocols. For static routing protocols, even though it's easy to configure, because I don't need to exchange any messages between the routers. The administrator, the system administrator or the network administrator will have to go into each router and configure the routing table on this router. So it tells this router that if you have any packet with destination address X, you need to go this way. If you have a packet with destination address Y, you need to go to this direction, and so on. The administrator is the one who will do that. There is no messages exchanged, and the best path is actually decided by the system administrator. Okay? So in that case, there is no extra resources needed. I don't need to receive messages and process these messages. So I don't have to exchange messages between the routers, right? So messages, they require some processing. When I receive a message, or when I receive a group of messages, the first thing I need to do is just to read this message, process it, understand what's the information contained in this message, and then update my routing table accordingly, right? In static routing protocols, I don't have to do that, because there are no messages exchanged. So, so it's easy to configure, and it doesn't need any extra resources, and it's more secure. Why more secure? Because I don't need to exchange messages, because what typically happens in dynamic routing protocols, and it's one of the biggest issues in dynamic routing protocols, that if there is any eavesdropper, he or she can listen to these messages, okay, and then extract the network topology based on these messages. And then disguise or try to pretend that it's one of the legitimate routers in the network based on knowing this topology. But for the case of static routing protocols, there are no messages exchanged. So the only one who can access these routers is the network administrator. Okay? Therefore, there's no, if there is any eavesdropper, he or she will not be able to listen to anything because there are no messages exchanged. So no one can actually collect information about the network topology. So therefore, the static routing protocols is more secure. However, there are fundamental disadvantages in static routing protocols that prohibit the wide usage of these static routing protocols in typical networks. Because network changes, they require manual reconfiguration. So if I have a network like the one in the university here, it's a very large network. Any change that happens in any single network in any lab, it requires the network administrator to go and reconfigure these routers, the routers that are affected. Otherwise, the network will not function properly. So this becomes really, really challenging, especially if we're talking about large topology. Like if we talk about a network in a lab composed of 2 or 3 routers, it's fine to use static routing protocol. So if there is any topology change, it's contained, it's lab-based, so all the 3 routers are in the same location. It's easy for the network administrator to go and change the routers that are affected by this topology change. But if we're talking about very large network, then it becomes really prohibitive for a network administrator to go and figure out which routers are affected, what is the location of these routers, then he or she should go to this location and fix these routers. Because of the scalability of the internet, static routing protocols are really, really used in a very, very limited fashion. Because the internet is all about scalability, it's all about large networks. Okay? So therefore, static routing protocols, even though it's attractive from this perspective, but it cannot be widely used. Okay? So therefore, dynamic routing protocols seem to be the answer for practical networks nowadays. So, but again, because of the scalability of the internet and the large, very, very large networks, we cannot use one unified dynamic routing protocol for all the networks. So what happens if I have a specific network with a specific routing protocol that talks with another network that uses different routing protocol? First of all, is that possible or not? If it's possible, okay, what is the boundary of a specific routing protocol? What are the different types of these routing protocols? So dynamic routing protocols are grouped according to certain characteristics, which we will talk about in a minute. Some examples for dynamic routing protocols are Routing Information Protocol, or RIP, Interior Gateway Routing Protocol, Enhanced Interior Gate Routing Protocol, Open Shortest Path First, Intermediate System to Intermediate System Routing Protocol, and Border Gateway Protocol. These are different dynamic routing protocols, but they are not the same. These can be divided into different categories. So, for example, we see that, first of all, dynamic routing protocols are divided into 2 categories. One is the interior gateway protocols, and the other is exterior gateway protocols. Under the interior gateway protocols, we have 2 categories. We have distant vector routing protocols, and link state routing protocols. An example of the distant vector routing protocol are RIP, either RIP version 1 or RIP version 2, and IGRP or EIGRP, and so on. For link state routing protocols, we have ISIS or Open Shortest Path First or OSPF. For exterior gateway routing protocols, we have the border gateway protocols. So we'll talk about we'll talk about some of these protocols in details in this part. Okay. So we need now to understand what is the difference between interior gateway protocol and exterior. So from the name, as the name suggests, interior, which means internal. Internal to what? So we need to know internal to what? And exterior to what? And what is the difference between distant vector and link state? So in order to understand the difference between these different categories of routing protocols, we need to agree on certain definitions first. Okay? So that's what we need to talk about now. The first definition is what we call autonomous system. As we all know, the internet is very, very, very large, right? To facilitate the scalability and the large internet communication, we cannot really say that the whole internet is just one network, one unified network. We cannot do that. Because if we can say that, if we assume that we say that the internet is one unified network, what is the network authority? Who is the owner of the internet? No one. There's no one owner for the internet, right? So if we talk about dynamic routing protocols, the dynamic routing protocol itself, we say that the dynamic routing protocols are used to exchange messages. But it becomes really prohibitive to exchange messages between all the routers on the internet. It cannot be done. Because in the internet, we have millions and millions of routers. So in order for a router connected to the internet to know the whole topology of the internet, it's really prohibitive. It's really, really hard, right? No matter how complicated the CPU or how complicated the computation facility in this router. Okay? So in order for us to kind of limit or make the routing protocols scalable, we define the concept of autonomous system. What this autonomous system defines is that it defines a boundary of a specific group of routers which lie under the authority of one owner or one person. For example, Ooredoo, they have a specific group of routers that they can control, which is the internal network of Ooredoo. Okay? So a service provider like Ooredoo has a group of routers, and these are defined within the boundary of what we call autonomous system. So autonomous system defines group of routers under the same single authority. Okay? So for example, I have a cloud like this. This is the Ooredoo cloud. So I have group of routers here, and this is what we call autonomous system. The autonomous system of Ooredoo has a specific identifier or ID, autonomous system number, as we will see later. And it defines itself as group of routers under the authority of Ooredoo. Then if I need to talk to another network, let's say AT&T network, AT&T has a specific autonomous system, and then we can communicate from this autonomous system to this autonomous system. Okay? So autonomous system, in other words, defines a boundary. Why do we need to define a boundary? Because then each of the routers inside that boundary, they need to understand the topology only within that boundary. They don't need to understand the topology of AT&T autonomous system. These are hidden from each other. So each router here will have to understand the topology inside this network, which means it exchanges dynamic routing protocol messages with all the routers within this autonomous system. Okay? So this makes the domain of exchanging routing messages limited. And that's really a must, because otherwise you end up with a flood of messages on the whole internet, which is not really scalable for very large networks. Okay? So the first thing we define is what we call the autonomous system, or the boundary of group of routers under the same owner or the same authority. Based on that autonomous system, we can then define, or we can understand the difference between interior and exterior gateway protocols. So interior here means interior with respect to the autonomous system. So interior gateway protocol define the routing protocol internal to the autonomous system, whereas exterior gateway protocol defines the routing protocol that facilitates the communication between two autonomous systems. Okay? So in other words, interior gateway protocols are used for intra-autonomous system communication, which means internal to the autonomous system, whereas exterior gateway protocols are used for inter-autonomous system communication. Okay? Any question, any confusion? So examples for interior gateway protocols, as we said, and these are protocols which are used within one autonomous system only. Once you go out, these interior gateway protocols become unusable. Okay? And then you use the border gateway protocol, an example for exterior gateway protocol, for exchange of communication between two autonomous systems. Okay? So in other words, if I want to send a message from this router, for example, to this router does not know anything about this router. All it needs to do is to know the fact that this message does not exist in this autonomous system. So it uses the interior gateway routing protocol, for example, RIP, to send this message to a border gateway, or they call it edge gateway or edge router. So if this message is outside the autonomous system, it knows that it should send it to an edge router. Okay? So for that, it uses the interior gateway protocol, or RIP. Once it reaches to that edge router, this edge router knows that this message should go to this autonomous system. Again, it doesn't know anything about this router, but it knows somehow that this message should go to this autonomous system. Based on that, it sends it to this edge router. This edge router will then use the interior gateway routing protocol inside this autonomous system to send it to the specific router. So I have to do that using 3 steps. 2 of these steps use interior gateway protocols, and then the intermediate step uses exterior gateway protocol. That's how it's done. So this definition of autonomous system allowed me to make it more scalable or hierarchical. Within one autonomous system, you can use RIP or OSPF or EIGRP or something like that. Between two autonomous systems, you have to use exterior gateway routing protocol, such as border gateway protocol. Okay? So that's what this definition here explains. So interior gateway routing protocol, it's used for routing inside an autonomous system, inside one autonomous system. And it's used to route within the individual networks themselves, inside the autonomous system. The networks inside that autonomous system. As an example, REP or EIGRP or OSPF or ISIS, all these are interior gateway routing protocols. Exterior routing protocols, such as border gateway protocol, it's used for routing between the autonomous systems or inter-autonomous system communication. Okay. So within the interior gateway protocols, we can further classify the routing protocols, as we said, into distant vector and link state. So what is the difference between distant vector routing protocols and link state routing protocols? That requires a little bit of focus, because this is one of the major points based on which the whole dynamic routing protocols are designed. So pay attention to that. So distant vector routing protocols, they use routes which are advertised as vectors. And the vector is defined by a distance. For example, this router advertises to all the neighboring routers the distance of all the networks connected to it. So it defines the distance to, if for example, there is like a LAN connected here. So this LAN is directly connected to the router, which means that the distance is 0. Okay? And then this router is connected to this router through this link. So this router needs to send to this router and this router and this router the distance between router 2 and router 4. In other words, this router 2 collects a vector of distances to all the networks that are connected to it, and then it sends it as one hop broadcast to all the neighboring routers. Okay? So that's how the distant vector is, that's how it works. Based on that, the distant vector routing protocols do not have complete view of the topology. What does that mean? The router R2 will send to R1 the distance between it and R4. R1 will then get the fact that if I need to send anything to R4, I need to send it in this direction, and the distance between me and R4 is, let's say, like 4. That's it. That's all it knows. It doesn't know the whole path between R1 and R4. It doesn't know that. And this is one distinguishing factor between distant vector routing protocols and link state. Okay? So R1, if it wants to send to R30, let's say, it knows one thing. It knows that the distance between it and R30 is, let's say, 400. This is the distance. And if I want to send to R30, I need to send to R2 first. Okay? But how is R2 connected to R30? I don't know. And I don't need to know. So maybe R2 is connected to another router, which is connected to another router, which is connected to another router, which is connected to R30. I don't know all this. I don't know the whole topology of the network, and I don't care. All I need to understand is the fact that the distance between me and any router in the network, the distance, is a specific number. And if I want to send to this, I need to send to one of the neighboring routers. That's all I need to know. But how is this router connected later on? I don't know. Which means that I have incomplete view of the network topology. I have only limited view of the network topology. Okay? That actually, in some cases, creates some problems for the distant vector routing protocols. One of the very common problems in distant vector routing protocols is routing loops. Because I do not have a complete view of the topology, I can send it to this router. I can send it from here to router 2. Router 2 knows that if it wants to send to router 30, it needs to send to router 4. Router 4, for some reason, because there is some inconsistency in the network, it knows that if it wants to send to router 30, it needs to send to router 1. So what will happen now? Router 1 will send to router 2, router 2 will send to router 4, router 4 will send to router 1. And it keeps looping like this. Because I do not have complete view of the topology. So I don't know, there's no guarantee that if I send it to router 2, that the message will in fact reach to router 30. I have limited view of the topology. And I have nothing that tells me that if I send a message in this direction, that there is a guarantee that it will reach to the ultimate target. There's no guarantee. Each one has limited view. So each one will route the message or will route the packet based on this limited knowledge. So that in certain cases creates this routing loops. That's one of the very common problems for distant vector routing protocols. In general, these vectors or this advertisement of the distances happens generally periodically. Okay? Which means that, and this is another problem in some of the routing protocols under the category of distant vector, is that it generally uses periodic updates. For example, REP uses every 30 seconds, it collects blindly all the distances in the local region, and then it broadcasts to all the neighboring routers. Okay? So what is the problem here? If there is any network change happens within this 30 seconds, I will not know about it until the end of the 30 seconds. Okay? Because the exchange of routing messages is periodical. Okay? That's why some of the routing protocols in this category, they try to resolve this by facilitating the periodic update, but if there is any network change, then it sends out of period update message as well, just to update everyone about the new topology change in the network. Did I answer your question while I'm talking?
So if I want to send from R1 to R30, I have to go to a neighbor R2?
Yeah. يعني زي ما بيقولوا كده طريق ال1000 ميل يبدأ بخطوة. I have no idea. I cannot jump directly to R30. Right? Can I? I don't have direct connection. So I know that I have direct connection with R2. I have direct connection with let's say another مثلا router here. So I have to make a decision whether to go this way or to go this way. Okay? Based on the fact that router 2 has a distance to R30, which seems to be better than this router, then it looks to me like it's better to go this way. But when I do this, do I have a guarantee that I will really reach to router 30? I don't.
How did the router choose which way to go if he doesn't know if this will get him to R30 or this way?
That's a good question. So what happens is that router 2, it sends me an accumulated distance between it and router 30. And it knows this accumulated distance through for example, it came from this router. This router sends to router 2 the accumulated distance between it and router 30. How did it know that? Well, again, it got a message in the past from this router, that the accumulated distance between this router and router 30 is good, which again got it from. So these distances, they get incrementally accumulated. Okay? So at some point, router 1 will receive a distance from router 2 and will receive a distance from this router. It will receive multiple distances between these routers and router 30. So basically the decision is based on which one is less. So if you know that in order for you to move from here to Duhail roundabout, then you can go to this direction or you can go to this direction. So if you know, assuming that you have real-time information of everything, then you can know that the accumulated distance between you and Duhail through a certain direction is better than another direction. Then you take the decision to go to this direction. Okay?
So doctor, if it's like this, why does it reach a point where it might loop forever?
Right, because what happens is that when you start forwarding a packet, it goes to this router, right? How does the router know which direction it should send the packet through? It consults what we call a routing table. We didn't talk about that yet. Okay? This routing table should contain the information which I have gathered in the past through these distances. But there is some possibility that these routing tables are not consistent. For example, when the system first starts, okay, maybe the information is not updated in all routers yet. So this router knows that the best distance to R30 is through router 2, but router 2 knows that the best distance for R30 is through router 1. Because the two tables are not updated yet. Okay, we'll talk about the definition of conversions after that. So if that scenario happens, and it may happen in practice, then we have what we call a routing loops. Okay? So these are the features or the characteristics of the distant vector routing protocol. We have vectors of distances and directions. So all I need to do is to know the actual distance between me and any router in the network, and this distance does not necessarily give me all the information about the topology, right? This distance is accumulated distance, but it doesn't give me any information about how I'm actually connected to this router. Okay? So it's as if you use Google Maps, then it gives you information that I'm going to, let's say, Education City. So go this way. Okay? So you give it the ultimate target, and it gives you local information. Go this way. Maybe the actual map is not it's not in your head, right? But you believe that if you go this way, you will at some point reach the Education City. so you trust Google Map. But it may be that you reach somewhere and then you go into loops based on the fact that you go in a certain position and then you see construction. So you go and you take a U-turn and then you go somewhere else, so you find some construction. So in that case, you end up having to go through loops. And actually, Google Maps tells you to go through loops because it does not have any updated information about the current situation, that there is in fact some construction here, there is in fact some construction here. This is what we call that there is a network topology, and maybe the propagation of this network topology change did not reach all routers yet. Right? So based on that, you start taking local decisions, and it's not right, it's not consistent. So it causes you to have to go through loops. So in that case, if you listen to Google Maps, you will go into a loops forever. In order to break this loop, you have to go with your mind a little bit. You have to take another route and to take some risk that this route will get you somewhere. Where you can use Google Maps, and then Google Maps would then have some consistent information that would help you to get to the target. Link state routing protocol, on the other side, is a little bit different. I don't actually send distances between the routers, the neighboring routers. And I do not host any routing table. I do not host routing tables inside the router. Okay? Based on accumulated distance. So what do I use? I have to exchange the state of this link. I have to propagate the state of this link to all the routers in the network. Not accumulated distance in that case. So, for example, when R1 sends to R2, the fact that I have a link between R1 and R2 with a specific metric or a specific cost, R2 will not accumulate that. R2 will send the message as is to all the neighboring routers, which means that R4 will get one message from R2 about this link and will get a separate message from R2 about this link. So R4 now knows that there is a link between R2 and R4, and there is another link between R1 and R2. And these are propagated or communicated through different messages. There's no accumulation in that case. Each link state, that's why it's called link state. Each link state is communicated through a separate message. Okay? So R2 will send message about this link, will send message about this link, will send message about this link, and it will send it to R3. R3 will collect all these three messages. It will not accumulate anything, will send all these messages to all the routers beyond it. Which means that link state routing protocols promote the fact that all the states of all links should be communicated to all routers in the autonomous system. So if you have the states of all links, you can sort of construct the topology. You can have a whole map about the topology. For example, Google Maps can tell you, okay, if you want to go to the education city, here is the path, and it gives you the whole thing. You have to go to this street, and then from this street you have to go to this street, and so on. So if you know all this information, and if you know the state of every single street, you can sort of draw the whole path in your mind. Right? So that's what link state does. It actually propagates information about all the states of all links in the network to all routers. Okay? So that's one major difference. So you have complete view of the network topology because you have separate information about every single link in the network. Okay? So instead of hosting a routing table is in the format like for a specific destination address, 1, go to router 1. This is for distant vector. This is the routing table, how it looks like, simply. If you want to go to destination address 2, go to router 1. If you want to go to destination address 3, go to router 3. Or go to router 2, whatever. So this does not give you any information about the topology. All I know is that I have to take an incremental step either in this direction or in this direction. So this is the routing table for the case of a distant vector routing protocol. For link state, you don't have this. You have one link, so router 1, router 2. This is a link and if specific information. Router 1, router 4 and specific information. Router 1, router 5 and specific information. So you don't have routing table per se. You have a lookup table of all the links. So you know if I want to know all the neighbors of router 1, I can know it. So router 1 is connected to router 2 and router 4 and router 5. So I know that this is router 2, this is router 1, this is router 4, and this is router 5. So later on, I can get all the neighbors of router 5. So I know whether there is a link here or there's no link here, and so on. From the link state table. We call it a link state table, not a routing table in that case. So this is a link state. This is a link state table. So link state routing protocols do not host routing tables per se. They host what we call link state table. From the link state table, I can construct the whole topology of the network. So if I collect the state of every individual link in the network, then naturally I'm required, if there is any change in this link, I have to report it right away. Okay? So generally, link state routing protocols, they tend to have updates based on event, which we call event-based update, or trigger-based update, not periodic in that case. So normally, link state routing protocols, they use event-based updates. Okay? So this is the between link state and distant vector. As we said, for link state, we don't exchange distances, we exchange the link state, and this link state will have to be collected individually. Nothing is accumulated in that case. And all the link state will have to be stored individually in what we call link state database in every single router. Okay? Another classification of the dynamic routing protocols is what we call classful and classless. And I assume that we are all familiar with what classful means and what classless means. So for classful routing protocols, the IP address itself indicates the class. As we have studied in 455, we have class A, class B, class C, and class D and class E are used for multicast and so on. So for example, if the highest byte, because IP has 4 bytes, the highest leftmost byte, or 8 bits, If this byte is between 0 and 127, then it's class A, if you remember. If it's from 128 all the way to, I don't know, like 196 or something like that, then it's class B, and so on. Okay? So the IP address itself indicates the class. So the routing protocols that were designed in the past were based on this notion. People in the past, they felt that the IP address domain is very large and we will never consume it, and so on, which طبعا turns out to be a myth. So they said, okay, so we have classes, and class A people are like supreme or VIP people. Very few people in the world, they have class A addresses, like Microsoft, like IBM or something like that. And each class A will have, up to 2 to the power 21 hosts in the network, which is extremely large. The good thing about classful IP addresses is the fact that we don't have to deal with subnet mask. And again, I assume that you know what subnet mask means. If you don't, then you have to go to 455 and really get some information about subnet mask. Later on, of course, people started to feel the contingency or the limited domain of IP addresses. So they started to invent what we call variable length subnet mask and so on, in order to remove the classes. So they said that we have to live in democracy, or people are equally weighted. So depending on your demand and depending on how much you pay, you get specific number of classes in your network, or specific number of IP addresses in your network. And you specify the number of addresses by allocating a certain subnet mask for you. A subnet mask is basically a continuous set of ones and zeros. So the number of ones, if the number of ones increase, this means that the number of hosts in your network decrease, and so on. So this is what we call classless. So similarly, routing protocols were divided into, again, classful routing protocols and classless routing protocols. Classful routing protocols, again, because we say that the IP address itself indicates the class. So there is no need to communicate the subnet mask. In other words, the routing protocol messages itself will not have to contain any information about the subnet mask, because the IP address itself will indicate the class. If the highest leftmost byte is between 0 and 127, we know that this is class A. Based on that, we know that there's 1 byte for the network, and the 3 bytes are for host. So 3 bytes are for host, which means that we can calculate the subnet mask easily. So I don't have to really communicate explicitly the subnet mask inside the routing updates. Okay? So REP version 1, for example, uses only classful routing protocols, which means that the messages do not have to contain any information about any subnet mask. And that's the only mode in REP version 1. Later on, they discover that classful routing protocols and classful networks are not efficient, because it promotes discrimination. Why do we have to designate people, very few people all over the world, as class A? So that divides the whole internet into fewer number of networks, and each of these fewer number of networks will have very large size of hosts, and maybe this network does not actually utilize all these hosts. So in which case we waste many IP addresses for no reason. So in that case, they started to communicate what we call the subnet mask. And subnet mask 24 means what? 24 means simply I have 24 ones, okay, and then 8 zeros, or actually less than 8, because it's 32. 8 zeros, yes. ماشي? The 24 ones and then 8 zeros. For example, subnet mask of 30, this means 30 ones and then 2 zeros. Okay? So for classless, now I have to send the subnet mask as part of the routing update, which is an overhead, but this overhead I have to do it for a reason. Because then I can use the IP addresses more efficiently and divide it between the different networks much more efficiently. So that reflected some changes on the dynamic routing protocols, that now the routing protocols will have to exchange subnet masks as part of the route updates. And this is very important. Okay? Okay. Another very important definition is the concept of conversions. Conversions, what does it mean? Conversion means that basically the routing information, whether this routing information is contained in a routing table or in a linked state database. Okay? This routing information inside these routers are all consistent. Yani consistent, that if there is any network change, such as, for example, this network is down, depending on the dynamic routing protocol you use, router 2 is the one that will feel that this network is down. Okay? So initially, router 2 knows, but router 1 and router 3 will not know that until they get some update from router 2. Okay? So initially, router 2 knows, router 1 doesn't know, and router 3 doesn't know, which makes the whole network inconsistent. For example, if router 1 wants to send to this network, it knows that it has to send to router 2. Router 2 will get this information, and depending on whatever routing protocol you use, it may actually send it here, because this link is down now. So this link has been removed from the routing table. Okay? Then either router 2 will say, I don't have any distance to this table or to this network, so I will drop the packet, which is better, because the other alternative is that I will say, I have very large distance to this network because I'm not connected to it at the moment. Because maybe, you know what? Maybe this network is actually connected to another router. Okay? Which is not directly connected to R2. So if this link is down, router 2 will say, I have very large distance to this network, so I will send it to router 3. Router 3, by mistake, takes a decision that, again, I don't have the direct connection to this network, but I know that you may actually be able to go to router 1. And then the loop happens. Okay? Conversions talks about the fact that loops should never happen because all the routing information in all the routers are consistent. They will never lead to any wrong decision. Okay? That if there is any topology change, router 2 informs router 1, informs router 3, in that case, all of them are informed. And this is what we call conversions. Okay? So conversion means that all the states, all the routing information in all the routers are in a consistent state, which should never cause any wrong routing to happen. Should never cause any loops or any mistake in routing the packets. Okay? Any questions here? Based on the routing protocol that you use, you may actually get some slow conversions or faster conversions. Why? As we said, a protocol like RIP uses periodic updates, right? So if this link is down, I will have to wait for 30 seconds because I use periodic updates. I don't actually report the change once it happens. I have to wait for 30 seconds. So after 30 seconds, router 2 will then form the distant vector and then will send it to all the neighboring routers. If there is another router here, again, it will not know that. Then it has to wait for 60 seconds, 30 seconds, and then 30 seconds again, for router 3 to inform it about the fact that this network is down. And if there is another router, then it has to wait for 90 seconds, and so on. So usually for certain routing protocols like RIP or IGRP, because it does not provide any event-based updates, the conversions in that case is slower compared to EIGRP and OSPF. As we will learn later, these two protocols, they use what we call event-based updates. So if there is any topology change, it doesn't wait. It sends the update right away. Okay? So in that case, R2 will send right away to these two routers. R3, because of the topology change, it will send right away, and so on. So I don't have to wait for 30 seconds or 60 seconds or 90 seconds and so on. I get updated, so if there is any topology change, the topology change will propagate in the network very fast. In that case, the conversions is attained in a faster way. Any questions? Routing metric is the way for me to evaluate the best path. As we said, I need to know the direction where the packet should go to, and that's based on whether this direction is better than this direction. So for me to decide that this direction is better than this direction, I have to have a quantity or a value based on which I decide to say that this route is better than this route. To go to the education city through this roundabout is better than this street, for example. So this is what we call the metric. The metric is a quantity, is a value, which is the distance. The distance is quantified in a form of a metric. This metric can simply be the number of hops. For example, router 1 has a metric or has one hop distance between router 1 and router 2. Router 1 has 2 hop distance between router 1 and router 3. Okay, so that's the metric. The metric is simply defined as the number of hops. This is one hop, and this is one hop, and so on. Which means that all the hops are equally weighted. Okay? That's what, for example, RIP routing protocol uses. So RIP version 1 and version 2, it uses the hub as the metric to decide the cost for a specific path. But is this really the best way? Do we have all these networks are the same? All these links are the same. Remember that between R1 and R2, I could use, for example, 1 gigabit Ethernet. Between R2 and R3, I could use only 100 megabit Ethernet. Or I can use wireless. This link could be wireless. So the link between R1 and R2 could be optical. Right? But if we use the metric as the number of hubs, then simply we deal with all networks as equally. Okay? Regardless of the bandwidth of this link. Maybe this link between R1 and R3 is 4G. And this link is 3G. So to use the metric as the number of hubs is not necessarily efficient. It's simple because I can calculate it easily, but it's not necessarily efficient. To deal with these links more efficiently, then I have to get more information. Then you have to tell me that this is 4G and the bandwidth of 4G is, for example, 300 megabits per second. So in that case, you use the bandwidth as the metric. So this metric could be simply the hub, the number of hubs, could simply be the bandwidth. If you know that this is, for example, a network with a specific type, and you know the bandwidth of this particular technology, or it could be a cost. For example, this cost could be the cost for transferring a stream of packets between you and Ooredoo, depending on whatever plan you have. Okay? Or the cost could be a combination of some of these metrics together. This metric could be the delay. The delay is the time taken to send a packet across this link, which is dependent on the bandwidth. Could be the number of hubs, could be the load, depending on whether this street is crowded or this street is empty. Could be based on reliability. Reliability, which means that what is the probability of failure on this link? Maybe I'm sending something to Google, so Google is very reliable, so I need to send it through a link which is highly reliable. If I send it to the server in XYZ lab, this is highly unreliable. So the communication there may go down at any point in time. Okay? So we'll continue next time, inshallah.